All right, hello everyone. In this video, we are continuing our discussion on measurement techniques and aspects of measurement that need to be kept in mind throughout the course, both in terms of doing experiments as well as studying theory. So, in our last video, we had discussed about errors and uncertainties and how they are different, and I had also drawn a line between accuracy and precision. So here we start off again from where we left off. Uh, Errors, like we said, were the distinction between a measured value minus the, or difference between the measured value and the expected value, which can be a universally accepted theoretical value or a literature value, as we call it. So that's what errors are. Now here we have two broad categories of errors that we generally encounter: the random error and the systematic one. Now random errors are errors that really cannot be eradicated completely. Okay. Now, what are the physical causes? What are the plausible causes that this might arise? One, the readability of the instrument means maybe the scale was skewed at that point, so you could not read it properly. Maybe the lighting in the room was insufficient for you to read it, especially if you're doing an optic experiment and you're doing it in a dark room. Then the scale needs to be clearly visible for you to make a proper judgment of where the measurement lies. The readability of the instrument, the effects of changing, of some change happening in the surroundings between measurements, which probably was not taken into account. Maybe you're doing a thermal physics experiment and somebody decides to switch the AC on, whereas you wanted to keep the temperature constant, and you had, maybe done or made some setup that kept the temperature of the room constant, temperature of the setup constant, or somebody switches the AC off. I mean, like keeping the AC on is probably a very good idea of maintaining thermal equilibrium in the surroundings. So, and they quickly realize their mistake and then they switch it back on. But by then the damage has been done. So you maybe took a couple of readings between that time, which showed a deviation from the original trend, as might be visible on your graph. Next, the observer being less than perfect. So, of course, being careless while taking measurements is something that is not recommended. So, if you have any trouble reading the instrument and you are aware of that, then please report and try and get it fixed. And please be aware of the precautions that you need to take while taking the measurements, right? And be consistent in what you do. Now, how to reduce random errors? They can be reduced by averaging. Now, of course, you say have an independent variable x, and you have three sets of dependent variable y. Basically, you take three trials, right? You might have heard your teacher say, take three trials of each reading. So x, and at x, you take three different readings. Okay. So maybe it's a reading for time period of oscillation of the pendulum. So you have y1, y2, y3, and you take an average of the three and you get an average value. So that's your data for x and y. So that's one, that's your one. For two, you repeat the same exercise, one and two, and that's how you continue. And finally, you end up with a set of data for x and y. Y has been averaged over here to account for the random error in y being negated by means of calculating an average. Okay. Now, please remember that repeating the results improves reliability. So if a question asks you, how do you reduce random error? Do not say, take more trials. The total thing that you mention over there, the entire thing that you mention over there is take more trials and calculate an average. So it is then and only then that random error is reduced. All right. Now, this is a result of the fact that when you take data, the spread of the data is governed by a lot of statistical factors. And those of you who are aware of statistics, or those of you, even if you're not, you might have come across averaging techniques like calculating mean, calculating median, calculating mode, right? All these are methods to find out one value to represent the entire data set, right? So a central value. So here too, we are doing the same thing by calculating y1, y2, and y3, or measuring y1, y2, and y3, and then calculating an average. We are representing the entire set of y1, y2, and y3 by this y average every single time, right? And instead of having 3 data points, we have 1. And this sort of negates the random error to a great extent. So, of course, you understand, if I were to take 10 trials of this, then the average would have been way closer to the actual result. So random errors can be reduced by averaging, and a precise experiment has small random error. All right. So this statement needs to be understood. A precise experiment implies that the values that you have, okay, they are not very far apart, right? So say if I were to draw a graph, right? So say these are the points compared to say this graph. These data points are more randomly oriented than these. Of course, that implies that this has more random error than this, right? Which means the precision of the instrument has been compromised one way or the other. All right. But please remember that it is in no way related to accuracy. Randomness of an experimental data set can, you know, can never be completely eradicated, like I mentioned before. It always exists. So there's no way that you will have a data set that is entirely non-random. Okay, averaging is just a means to reduce it. Right. So next we come to the other error that we encounter, systematic errors. So maybe you have a data set from a previous experiment using the same setup, and then you do the same experiment again to check for the reliability, right? You're repeating it. But somehow you are ending up with different data points for the same independent variables. And you're baffled as to why is this happening. It can happen for any of these reasons. The instrument is wrongly calibrated. The instrument that you worked with probably was tampered with after the previous experiment was done, and now it has calibration error, right? So maybe the scale has been tampered with. So the 0 is not where it should be. The 100 is not where it should be, right? So it's a problem. It's a fault with the instrument. Or if it's a thermometer, then maybe there are some impurities that have crept up within the instrument, right? If it's a meter, maybe there's a short within the meter that is causing the meter to malfunction. Next, an instrument with a 0 error. So sometimes you see that certain scales, they especially in a meter, say this is the meter, the 0 is here, but the scale starts from here, or the pointer is here before starting the observation. This implies that this meter has zero error because the 0 does not align with the pointer, okay, at the start. So if this were the case, then every reading that you take is actually less than the actual reading. So you add this part to your reading to get the actual data point. Similarly, if this is the case, then every reading you take is actually greater than what it is. So you subtract this part from each data and then you get the actual result. So systematic error is a lot easier to deal with. It's a lot easier to identify for us as an experimenter because we will know that it's consistent. And every data point is maybe shifted by 5 units up or down. So then we will know that the entire data set was compromised by a systematic error. And we look for it within the instrument, try and figure it out. Of course, the observer being less than perfect, the observer is always at fault. Human error can arise at any point. Okay, so systematic errors cannot be detected or reduced by taking more measurements. The only way is to figure out what was the cause within the instrument that resulted in a systematic error and account for it within your data in order to get more accurate results. So in order to come close to the theoretical values of the data set, you have to take into account the systematic error. And therefore, an instrument which is far closer, giving a result which is far closer to its actual value is low on systematic error. So here, if the readings are all clustered together and they don't have a huge spread like this, then the experiment is precise because it has small random error. And here, if the systematic error is small, then we can say that the deviation from the actual results is not quite as much. So the error is reduced, which means so it's quite accurate, right? So I would suggest that when you're reading this entire thing, make a mind map of errors, uncertainties, accuracy, precision, kinds of errors, right? And try and form your own understanding of these concepts because these will be used time and again, right? In fact, in paper 3, when you are doing your database questions, you will be using these skills quite often and they would come in really handy. All right. So with this, we come to the end of this video. In the next video, we will look at how to use errors and uncertainties while drawing graphs and link them to drawing and understanding the implications of the lines of best fit.